Started. Yes. Now, in this particular session, let us discuss problems related to multiplexers. As I told you in the previous session, like we are going to discuss different kind of problems related to multiplexers, like different categories of problems which we are going to discuss, right? Yeah. So first of all, let me share my screen. Yes. So in our previous sessions, we have completed about this comparators, and we have also introduced it to multiplexers and all, right? So as I've told you, we are going to discuss about something. One second. And as I've told you that we are going to discuss about this different kind of category questions, right? Like discussing about logic gates building using multiplexers, and we are going to build flip-flops using multiplexers that we are going to discuss after having the discussion with uh, flip-flops. And next, we are going to discuss about higher order multiplexers using lower order multiplexers. Yeah, this is what we are going to discuss. Okay. And one second. Am I audible in live stream? Yeah. Audio is also clear. Now, let us try to have the first category of questions. Let me change the color. Let's say suppose if I want to build a simple NOT gate using a simple 2 cross 1 mux. Can anyone tell me how many multiplexers do we need for implementing this NOT gate using a simple 2 cross 1 mux? What do you think? How many number of multiplexers do we need for implementing a simple 2 cross 1 mux? Any guess? My question is, how many multiplexers do we need for implementing a simple 2 cross 1 multiplexer? Only one. Exactly. Now, how to implement it? So we can basically take the equation of my 2 cross 1 multiplexer, which is nothing but y is equal to s complement into I0 plus s into I1. This is the equation of my 2 cross 1 multiplexer, right? Now, what do I need? I need to have a simple 2 cross, simple NOT gate where if I'm going to give A over here, I need to get A complement. Okay, this is my requirement. Now, what I can do, I can just simply substitute S is equal to A and I0 is equal to 1 and I1 is equal to 0. So if I substitute these values inside my equation, so what I'm going to have is Y is equal to A complement into 1 plus A into 0, so that I'm going to get A complement, which is nothing but Y. So this is how I'm going to get a NOT gate using a multiplexer. So I'm going to have a 2 cross 1 mux like this, and I'm going to connect I0 as 1 and I1 as 0, and I'm going to take select line as A, so that I'm going to get Y is equal to A count. This is how I'm going to implement a simple 2 cross 1 multiplexer. I mean, simple NOT gate using a 2 cross 1 multiplexer. Okay. Now, I am also have another method where what I'm going to do is I'm going to simply take the NOT gate truth table. So if I take the NOT gate truth table also, I can implement it. So how I'm going to implement, let us try to understand. So I'm going to take A over here, and this is my Y. Okay. Now your input, what you're going to have, if your input is equal to 0, your output is equal to 1. And if your input is equal to 1, your output is equal to 0. This is my uh, NOT gate truth table if I'm going to. So what I'm going to take is, let's say this is my select line. Now, if your select line, in this case, your select line is equal to 0, we know that we are going to connect I0. And in this case, my select line is equal to 1. That means I'm going to connect select line if it is equal to 1, I'm going to connect I1. So what is the value of I0? I can see it is clearly 1. And what is the value of I1? It is clearly 0. So from this truth table also I can get the values of my multiplexers. So I'm going to have this AND. Okay. So there are basically two methods you can use. One is directly using the equation, or another is you can directly use the truth table of the whatever the logic gate you want to implement, and you can get that particular implementation. Okay. Yes. Now let us try to implement this AND gate and using 2 cross 1 multiplexer. Now if I want to implement this AND gate using 2 cross 1 multiplexer, how to implement? Let us try. So what do you think? How many multiplexers do we need to implement a simple AND gate using a 2 cross 1 multiplexer? Anyone wants to answer? How many? Okay, only one. Okay, let's see. So using equation, it is going to be a long process. So I'm not going to use my method one, that is my equations. Using equations, I'm going to use the truth table method for getting my answer. So I'm going to first of all come with the AND gate truth table, which is A, B, and Y. What I'm going to have 0, 0, 0, 1, 1, 0, and 1. Here I'm going to get my output as 0, output as 0, output as 0, and here my output is equal to. And what I'm going to do is I'm going to consider my A as my select line. So here I'm going to consider A as select line so that I can see select line is equal to 0 and select line is equal to. So for this reason, continuously you have 0, 0, and 1, 1, right? So that's the reason I'm taking A as my select line. Now, if I'm going to take A as my select line, and then what is my Y over here? This is my I0, and this is my I1. Okay. Now, what is your I0? You can see over here. Whatever value of your B may be, maybe 0 or it may be 1, your output is equal to 0. That means I0 is equal to 0. Okay. Now, coming to my I1, you can see it is just a copy of your B. If your B is equal to 0, output is equal to 0, B is equal to 1, output is equal to 1. That means I1 is equal to B. That's it. So you have select line is equal to A, and I0 is equal to 0, I1 is equal to B. So I'm going to take a simple 2 cross 1 multiplexer over here, and I'm going to connect select line is equal to A, and I0 is equal to 0, and I1 is equal to B, and here I'm going to get A dot B. You can also cross verify with the Shannon's expression. So Y is equal to S complement into I0 plus S into I1, which is nothing but A dot B you're going to get. So this is how we are going to implement a simple AND gate using a 2 cross 1 multiplexer, and whatever the answers you have given, only we need only one multiplexer for implementing a simple uh, AND gate. Now, let's say suppose if I want to implement an OR gate or using 2 cross. Now, can anyone tell me how many number of multiplexers do I need for implementing this? How many multiplexers do I need for implementing a OR gate using 2 cross 1 multiplexer? One 2 cross 1 multiplexer. Okay, let's see. So I'm following again the method number 2, where I'm going to first of all come up with the truth table of my OR gate. One second, let me exit from this PPT. What up I do is yeah. So first of all, I'm going to come up with the truth table of my OR gate, which is A, B, and my output. So I'm going to have 0, 0, 0, 1, 1, 0, and 1. So here I'm going to get 0, 1, 1, and 1. Okay. This is my truth table of simple OR gate. And I'm going to consider the select line is equal to A. Okay. Here you can see your select line is equal to 0. And here our select line is equal to 1. Now, if select line is equal to 0, which is nothing but my I0. Now, what is the value of I0? If you carefully observe, whatever the value of B that is present, that is being copied to your output. That means I0 is equal to B. And what is the value of my I1? I1, if you see, whatever may be your value of B, your output is equal to 1. So I can write simply I1 is equal to 1. Okay. So that is what I'm going to write it down over here. I'm going to take a simple multiplexer, and here select line is connected to A, and my I0 is connected to B, and I1 is connected to 1. And I'm going to get over here y is equal to A plus B. You can also substitute in your Shannon's expression. You're going to get y is equal to A complement into B plus A, which is nothing but A plus B. Yes, exactly. Whatever the answer you have provided is correct. Only 1 2 cross 1 multiplexer we needed. Yes. And coming to this not and OR. Now coming to NAND gate. So how many 2 cross 1 mux do we need for implementing a NAND gate? Okay, let's verify. So I'm going to have a NAND gate truth table A, B, and Y, and I'm going to have 0 0 0 1 1 0 and 1. So here I'm going to get 1 0 0 0. This is my NAND gate truth table. Now I can see I can have this E as my select line, and here my select line is equal to 0, and here my select line is equal to 1. Now, if my select line is equal to 0, I can see uh, what is my output. So output is nothing but my complement of my B. So I can write I0 is equal to B comp. And here I can see whatever my B value, my output is equal to 0. So I1 is equal to 0. This is what I'm going to do. So for implementing B complement, I need one more multiplexer. So I need a multiplexer like this, where I'm going to have select line as B, and one of the input as 1 and another is equal to 0. So from here, I'm going to get B complement. This B complement is given to I0 pin, and select line of the second multiplexer is connected to A, and the second pin is connected to 0. So this is how we are going. So you can also cross verify with the Shannon's expression. It is nothing but y is equal to E complement into B complement, which is nothing but where have we done any mistake over here? Sorry, I am written the truth table itself wrong. Let me erase it. Yeah, truth table is wrong. Yeah, yeah. I've written the NOR gate truth table, not the NAND gate. So over here I'm going to get 1, 1 and 0. So if my select line is equal to 0, I0 is equal to 1. And here I1 is equal to B comp. Okay. So this is connected to I1 and this is connected to I0. I0 will be equal to 1. And if you cross verify with your Shannon's expression, you're going to get y is equal to A complement plus A into B complement. That means your y will be equal to A complement plus B complement. And if you apply De Morgan's law, you're going to get A dot B down. This is the NAND gating. So just reverse them, or else I have written I1 and I0. Okay. Yes. So this is how we are going to implement NAND gate using 2 cross 1. So for all two input problems, 2 cross 1 is answer. No, here we need 2 cross 1, right? Do you have any particular solution where we can implement a NAND gate using only 2 cross 1 nodes? If yes, please share it to me. Okay, Jiva? Yes. So let's move forward. And let's say if I want to implement a NOR gate using 2 cross 1 nodes. Previously, I have written a table, right, that is belongs to NOR gate. E, B, and Y. 0 0 0 1 1 0 and 1. So here I'm going to get 1 over here, and here I'm going to get 0 0 and 0. This is my NOR gate truth table which I'm going to have. And if my select line is equal to 0 over here, and select line is equal to, okay. Now that means my I0 will be equal to B complement, and I1 will be equal to, I'm going to have I1 is equal to 0. Okay. So this is how we are going to have. Next, let's implement XOR gate. using 2 cross. Now, first of all, let us have the XOR gate truth table A, B, and Y. So 0, 0, 0, 1, 1, 0, and 1. So I am going to have 1, 1, and 0. Now, here I am going to have my select line as A. So select line is equal to 0. If my select line is equal to 0, this is my I0. And here, this is my select line is equal to 1, which is nothing but my I1. Now you can see we are going to have the complement. So I0 is equal to B complement. And here, sorry, here we are just copying the B value. So it is I0 is equal to B and I1 is equal to B complement. Okay. So I'm going to have a simple 2 cross 1 multiplexer where I'm going to have select line is equal to A and I0 is directly connected to B and I1 is connected via the NOT gate B1 0. This B complement is connected and Y is equal to A XOR with B. This is what I'm going to do. Okay. Yeah. Any doubts or any queries over here? Yes. Now if I want to implement a XNOR gate using 2 cross 1, then how to implement it? Just to reverse the bits. That's it. So I'm going to have my select line is E and I'm going to have B complement over here and B over here. And I'm going to get A XNOR with B. That's it. Okay. So this is how we are going to implement all the logic gates using 2 cross 1 box. Okay. Now, let's say if I'm going to have the question as, let's say suppose if I want to implement a AND gate using 4 cross 1 box, then how are we going to implement? Let us see. So let's say I'm going to have the AND gate truth table again, A, B, Y, 0, 0, 0, 1, 1, 0, 1. It is 0, 0, 0, and 1. I'm going to have a 4 cross 1 mux over here. Okay. Where select lines I'm going to connect A and B. Where S1 is equal to A and S0 is equal to B. Okay. If your select line, if it is equal to 0, 0, you can see your output is equal to 0. That is the reason I'm going to give 0. And if your select line is equal to 0, 1, your input is equal to 0. And again 0. And for select line 1, 1, you're going to give the input as equal to 1. So here you are going to get y is equal to e dot. Just to replicate the truth table input outputs over as the input of your 4 cross 1 box, you are going to get. Exactly correct. We can write the truth table outputs as direct input in 4 cross 1 and we can use EB as a select lines. Exactly. So for all the logic gates, you can do the same thing. Implementing with 4 cross 1 mux and 8 cross 1 mux, it's very simple. Okay. For 2 cross 1 mux only, you need to have some kind of method. Don't try to remember the things using 2 cross 1 mux. Just try to remember the method. Okay. Then it will be easier. Yes. So that's about this particular session. And in our next session, we are going to discuss about higher order multiplexers using lower order multiplexers. We are going to discuss all these particular cases. Yes. So if you have any doubts or any other queries, you have it.